Okay. Okay. So today we'll talk about graph neural networks. It will be the end of this track where we were considering architectures that are specific to structured data. So we have seen already neural network architectures to deal with images. We've talked about CNNs and then more advanced architectures to deal with computer vision tasks. Then we talked about attention layers and transformers, which we've used basically to process sequences or sets. And today we'll talk about graph neural networks, which is an architecture to deal with graphs. So as soon as you have data which can be represented as graph, then you will be able to use this neural network architecture. And you will actually see that this architecture is very elegant in the sense that it's a generalization of basically everything that we have seen so far. I will already spoil you and tell you that an attention layer is a special kind of a GNN, that a convolutional layer is a special kind of a GNN, and basically almost everything can be represented inside a GNN. All right. So the menu for today will be to do first a brief recap about graphs, but I suppose you are quite familiar already with the graphs. Then we'll see how to ingest graphs into neural networks, and we'll see an architecture or basically building blocks that you can use to build the graph neural networks. I will also discuss a few special cases of this architecture, and we'll recover interesting architectures that we have seen previously. And finally, I will discuss a few really nice applications of GNNs in reality. Okay? So, but basically the motivation is simple. There are really many real-world problems that do not fit these tabular format representations, which you are familiar with. So in machine learning, usually we assume that we have input vectors of features, and then we want to predict some output. But in many cases, the input data cannot very easily or naturally be represented in the form of just a finite set of features inside a vector. Instead, what can be much more natural is to represent the input data as a graph. Okay, so for example, that would be the case of, let's say you want to build a machine learning model to process molecular structures. So you would have, for example, a number of atoms that are connected to one another, and you want to classify, for example, the molecular structures that they represent. And of course, what is a bit difficult if you were to use the regular tabular format representation is that molecules, they differ in the number of components. You may have very small molecules with just a small set of atoms, but you may have larger molecules with many more atoms. And so the question is, how can we have an architecture which will be able to deal with all kinds of graphs at once? So small graphs, bigger graphs, and so on. So that's the first application. Traffic networks is another example, which we'll see later on at the end. Scene graphs, social networks, even computer programs, you can view them or consider them as a graph where the nodes are the state of the program, and you have an edge between, for example, two variables. If there is an instruction which modifies or create variables given orders, and many other applications. Okay, but the example I will use mainly today is the case of molecules, because it's the mapping from the problem to a graph is really obvious in this case. A molecule is really naturally represented as a graph, where the nodes of this graph would be the atoms, and the edges connecting two nodes would correspond to the bonds between atoms. Okay? So, for example, you would have this molecule that you see on the left, and a representation in the form of a diagram is given on the right. Okay? And what we can also have in this kind of problems is that not only we have a graph which represents the data, but we may also have additional features that we associate, for example, to the nodes or to the edges. Okay? For example, in this case, we know that each node corresponds to an atom, and each atom comes with its specific properties, which we can encode as a set of features, which we associate to each of the nodes, okay, inside a small vector together with each node. And we can do the same for the bonds, so for the edges connecting two nodes. We can also associate features if we have or if we want, okay? And then an interesting problem could be one given these graphs that represent molecules, and this is just to motivate, but maybe something we would want is, for example, to feed this graph representation inside a neural network. And the goal would be, for example, to classify these molecules. For example, if you want to classify or determine if a molecule is a potent drug or not, okay, that's at the end of the day a classification problem, a binary classification problem, where the input correspond to molecules in the forms of graphs, and the output is just a binary label, potent or not. Okay? Yeah, okay. And so you may have a data set like this, where someone or a team of people have just evaluated, assessed the if a molecule, for example, has an effect on the growth of a bacteria. You collect the labels, and then you have a data set of inputs and outputs. And now you want to learn this mapping. Given a graph that represents a molecule, can you guess if the molecule will have an effect, a pharmacological effect in this case? Okay? And so you may think, but what's really is this really useful, or is this just an academic problem, an exercise for this lesson? Actually, it's not. So people have actually used this strategy to identify new drugs, new antibiotics. And really the issue with this problem of discovering new drugs is that if we were simply to consider all possible molecules that have a pharmacological effect, you would have to screen in the order of 10 to the 60 molecules. And then for each of them, you would have to do a wet lab experiment where you actually put the molecules and then you see if this is an effect or not. So practically, you can imagine very quickly that this is really not feasible at that scale. However, what you could do, if inside a computer you can already assess even only approximately if a molecule will have or is promising is a promising potential drug, then you can accelerate this process by quite a lot, and then just basically filter out or keep the molecules that appears to be promising, and then only then you do the wet lab experiment to actually verify if the molecule has an effect or not. And this is really a strategy which is used now in all pharma companies. Almost all of them have research teams trying to do drug discovery using neural networks, at least in software. And so, for example, this very approach that I'm outlining here has been used to discover a new antibiotics, allicin, which was known previously. So the compound itself was known, but people did not realize that it could also be used as a highly potent antibiotics. Okay, so this is very powerful in my opinion, with very nice applications. With what we'll see today, presumably you can use this technology to do great things like discover new drugs or new antibiotics. However, what I should also tell you from the start is that if you can discover new drugs, you can also discover weapons, chemical weapons. You just have to reverse the loss. Instead of identifying something which would cure, you can try to identify something which would kill. And people have tried that. So you can look at this paper, use the same technology, the same graph neural networks, and you can identify poisons that are really, really potent as well. Okay? So as always with AI, it's I would say a double-edged sword. You can do great things, but also you can very quickly also do bad things if that's your goal. Okay? All right, so that's what's for the motivation. Let's go back to the basics then and talk about graphs. and then we'll see how we can ingest these graphs inside neural networks. All right, so the first thing is, what do I mean as a graph? So a graph, and you should be, I suppose, very familiar with this. A graph is a tuple, it's a pair of two elements. The first is a set of nodes, V, and the second is a set of edges connecting the nodes together. All right? So we could have, for example, a graph like this, where we have, let's say, 5 nodes, okay, which I will, this is 1, 2, 3, 4, and 5, okay, and they are connected, maybe like this, okay, that's a graph. What we'll consider today is that, okay, we have these 5 nodes, and together with these 5 nodes, we have features. Okay, we associate to each of them small vectors of features. Okay, so that would be x2, x1, x3, x4, x5. All right. And what I will do is that I will put all these vectors into a big matrix, where on each row you have one of those vectors. Okay, so you have one row per node, and then you have one, the corresponding vector, or the transpose of the vector in this case, on the corresponding row. Okay? Then we also have the adjacency matrix, which will be a square matrix, where we have as many rows and columns as we have nodes. So in this case, it would be a 5 by 5 matrix, where it's full of zeros, except at the locations for which there is an edge connecting one node to the other. Okay, in which case the entry would correspond to 1. So for example, for this graph, we would have that node 1, okay, is connected to node 2 and 5. Okay, so I'm putting zeros everywhere, except for the second and the fifth element, okay, because there is a connection from the first node to these two nodes. All right? Then for 2, it would be connected to 1 and 3, and 5. For node 3, it would be connected to 2 and 4. For node 4, it's connected to 5 and 3. And for node 5, it's connected to 1, 2, and 4. Okay? And so the representation of graph that I will use today is this pair of X and A. All right? That will be my input graph. Okay? And I will not be talking about the case where we could have additional features to the edges, okay? But it's an extension of this. Okay, we would have a third element in this tuple, which encodes, in this case, all the features about the edges. Okay? Also, I will consider mostly today that the edges, they are not directed. Okay? So that's why in this case the matrix, the adjacency matrix is symmetric. But you can generalize of course to the case where the graph is directed, in which case, for example, here you see that node 1 is connected to 2 and vice versa, 2 is connected to 1, okay, because of these two entries. But you could say that you have directed edges, and for example, have put a 0 there, meaning that in this case there is, now the edges become directed. There is an edge going from node 1 to 2, but there is no edge going from 2 to 1 anymore. Okay? Okay. Questions so far? So for those of you who just arrived, so the goal today, just a quick recap, is to do to design an architecture of neural network that would be able to ingest this as input. And the goal would be, for example, to use that then to treat machine learning problems like classifying graphs or doing regression on the nodes or on the edges. And examples of applications I've quickly mentioned are, for example, the case of molecular predictions, where you would get as input a molecule, which you can naturally represent as a graph. And then you want, let's say, for example, to classify this molecule. For example, you want to assess if this molecule could be an interesting drug or not. Okay, in this case, and that's what we'll see today. You can do that with this kind of architecture. Okay? All right, so this is done. Okay, now what are the tasks we'll consider today? So given a graph, okay, which is this pair of nodes and edges, which I represent as this matrix of features and this adjacency matrix. Okay, what we want to do, so we can design several tasks now on top of these graphs. Either we want to make graph level predictions. So given the entire graph, we want to predict some output in a set of output values y. So for example, you would want to do the graph level predictions. Well, we want to predict some output y as using a function, in this case a graph neural network, that takes as input these two guys with so for example, in the case of classification, that would be the usual thing. For example, we want to associate a vector of probability estimates over a set of classes, or if you want to do regression, you just predict some scalar value given the input graph. Okay? Then we have node level predictions. Where you will have y now, which is a vector, okay, which you produce through a function which gives you a vector as output, okay, but it's still a function that takes the this representation of the graph as input, okay, and again now we will have this to belong to some set, which I will denote as y. Could be this one, or something else. But we have several elements in this vector. We have v of them, if v is the set of nodes, and so the cardinality of v is simply the number of nodes in the graph. Yes?
The figure one here is associated for each node in the graph?
In this case?
In the node level prediction.
Yes, so it's as if you take this whole graph as input, and then for each of the 5 nodes, you make a prediction. Okay? And finally, you have the edge level predictions, which is similar, except that now you make predictions for each one of the edges in the graph. All right? So on the slides, you see these 3 examples where you start, let's say, with this graph made of 6 nodes connected somehow, and you see together with each of the nodes you have a small vector which corresponds to the axis. And let's say the goal is to classify the graph. Then what we'll do today is to design an architecture, a graph neural network, which will be able to take this graph as input, then process the information, and the processing will be done by computing somehow new vector representations at each of the nodes. Okay. Then we'll have a second mechanism which will aggregate all these vectors somehow again. That will produce a new vector, and then finally from this vector that now represents the entire graph, we'll feed that as input to a next function, like a small MLP or something else, that will finally produce the output. Okay? For the node classification case, or the node level predictions, we do something similar, except that we basically stop before this step. We just recompute new representations of the node vectors. Okay, and then from these node vectors, we'll then compute the final predictions for each of the nodes, again using a small MLP or something else, but which will apply locally on each one of the node vectors, instead of aggregating everything, producing a vector, and then, and only then, feeding that as input to the classifier. Okay? And for the edge prediction, edge level predictions, again, it's the same, except that now we would have, we could have features for each node, also features or vector of features for each of the edges. Then we would compute representations for each of the edges, and then from these vector representations of the edges, we would apply locally a classifier to obtain the final predictions for each of the edges. Okay, so do you all see what we want, the kind of things we want to do today? Yeah? Okay, there is, however, one requirement, which is, okay, if you take this node, this graph, and then you just rename the nodes. For example, you say that node 1, you call it node 2 now, node 2, you call it node 5, node 3, you call it node 4, and so on and so forth. The resulting graph will still be the same. It's not because you permute, for example, you permute these vectors and you permute the adjacency matrix because you've renamed the nodes, that the graph itself has changed. Okay, is it clear for everyone that? So what I'm saying is that because of this representation, we are imposing an ordering on the nodes. Okay, we are saying that there is a node which will be the first, there is a node which will be the second, there is a node which will be the third, and so on and so forth. But this is mathematically not something that should be part of the graph representation, because a graph is this tuple of V, the set of nodes, and the edges. But these two elements, they are sets, so they are not ordering their elements. Okay, but when we switch to this representation, we are now imposing an ordering on the elements. Okay, which is bad. Okay, because it means that if really then we want to implement these two functions, we should make sure that if we permute the elements in these representations, the graph will not change. And so our requirements that we'll have is that if we permute the elements, the output, for example, of the graph level predictions should not change. Okay, if you rename the nodes, you get a new, up to some permutation, representation of that graph X and A, but the output of your graph neural network should not change. Okay, and similarly, if we are doing node level predictions, if we permute the nodes, then what should happen then is that the predictions for the node level so the node level prediction should permute in the same way as you have permuted the input elements. Okay, so mathematically, if we consider a permutation matrix, which will basically change the ordering of the elements in X and correspondingly in A, and you can do that by just having this kind of matrix, we will obtain a new representation of the graph. So for example, if we start with the previous graph, so this one, okay, and then I'm just defining a permutation of the nodes in the form of this permutation matrix, where I'm saying now the first node becomes the second node of the original graph, the second node becomes the last of the original graph, and so on and so forth. So what will happen is that I will just be permuting the rows of the X matrix, and you see that the second row becomes the first, the last row becomes the second, and so on and so forth. And so we obtain, by just permuting the rows, the new representation for the X matrix. And similarly, you can also obtain the permuted, you can permute the elements of the adjacency matrix to obtain the adjacency matrix of this new graph. And you can do that by multiplying to the right the adjacency matrix by the transpose of the permutation, and to the left by the permutation matrix. Yes?
Does it mean that our prediction model should be linear in order to preserve them?
No. I'm just for now basically defining what I mean by a permutation, and then I will at the next slide actually I will tell you about what should be the requirements on f and on small f and big f. Okay, but you agree that at the end, even though we have permuted the nodes, the graph itself is still the same. Okay, it still represents the same thing. Okay? And so one thing that we will require is what we call permutation invariance. Okay, so it's based on this idea that because, yes?
Yes, in order to have the same graph, after a permutation, we will have to apply the permutation on both X and A, not only on X or not only on A.
Yeah, of course. Yeah. What I'm just saying is that this graph, so for which we have this representation for X and this representation for the adjacency matrix, is the same as this one. Okay, even though we have two distinct representations, the X and the feature matrix and the adjacency matrix, they are not the same, but they represent the same graph. Okay, so what do we require? So what I was about to say is that because our representation through a vector matrix, through a feature matrix and an adjacency matrix impose an ordering of the nodes, which is in contradiction with the fact that in a graph we don't have any ordering on the nodes. Okay. What we'll try to design in our graph neural network is a property such that if we permute the nodes, the output will not change. Okay? So strictly speaking, for graph level task, we'll want permutation invariance, meaning if you compute some graph level prediction on some representation of a graph X and A, you will get some value. And what we'll require is that for this value to be equal to the output of the same graph neural network, but applied to the permutation of the representations. Okay? So if you apply the same graph neural network on the permuted feature matrix and the permuted adjacency matrix, which represent the same graph, okay, then you should obtain the same results. Okay? Because they even though, again, these representations are distinct, they represent the same object. Okay, and that should be true for all permutation matrices P. Okay? So this is for graph level task, we want permutation invariance. For the node level task, where we are predicting vectors or output values for each of the nodes, now if we permute the representations, we'll want the output to be permuted in the same way. Okay, so in this case, we'll want permutation equivariance, meaning that if we compute through F, big F, node level predictions, and then we permute them, we should obtain the same result as if we had applied F, this node level graph neural network, on the permuted representation of the input graph. Okay, so you start from the original representation, you compute some output for each node, then you permute them. You should obtain the same result as if you had started from the permuted graph, you permute first, and then you compute the predictions. The two results should coincide. Yes?
Is it the same requirement for prediction?
Yes, yeah, it will be similar. Okay, so that means permuting the nodes of the graph should modify the results, of course, but only up to the permutation. Okay, so far? Okay, so now we are ready. Now that we have defined a graph, we have defined permutations on the representations and some requirements, we are ready to introduce graph neural networks. And really, the blueprint is quite simple. So what we'll do is to define permutation equivariant functions, which will stack, okay? And then we'll follow, optionally, these permutation equivariant functions with permutation invariant functions if you want to do graph level predictions. Okay, and so the trick will be to design functions or layers that are permutation equivariant. If we shuffle the inputs, that automatically shuffles the output. And so if we can do that, then we have everything to basically produce node level predictions while satisfying our permutation equivariance requirement. And then if we can, in addition to that, also have layers that are permutation invariant. Okay, if we shuffle the inputs, that will not change the output. Then we can couple these layers with the previous one to obtain now graph level predictions that would be permutation invariant. Okay, so the blueprint for the GNNs that we'll see will go as follows. We'll start with some input graph, which is represented by, again, a feature matrix and its adjacency matrix. At each node, we'll have a small vector xi. Okay, that's the input graph. Then the idea will be to design some architecture, some GNN, that will produce a new representation of each of these vectors. Okay, so each vector at each node will be transformed into a new vector hi somehow. The trick, because we have graphs, will be to try to compute these latent representations or hidden representations based, of course, on the structure of the graph. And typically what will happen is that these edge vectors will be computed as a function of the connecting nodes, and specifically a function of the vectors associated to the connected nodes. That will produce new vector representations. And then from these vectors, okay, we'll define our tasks. So for example, if you want to do node level classification, then we'll take each of these vector hi in isolation, we'll feed that to another function, another neural network, to produce, for example, a vector of probability estimates. If we want to do graph level predictions, like graph classification, Then the mechanism that we'll use is to aggregate all the vectors that we have at all nodes. Okay, and we'll do that through some aggregation operator, which will be, in this case, permutation invariant, but I'll talk about that later. That will basically summarize everything into now a single vector of a known size, and then we'll feed this single vector, representing now the whole graph, as input to another function, which will produce the final classification output. Yes?
How each I is computed?
We'll see that later on.
Can you mention your XI?
I will explain things from top to bottom today, and so you will see shortly how it's implemented. I'm just giving you like the sketch now, and then we'll see how each of these elements is actually implemented or can be implemented. Okay, and if you want to do link predictions, so edge level predictions, then we would have, again, a function that now takes as input, for example, the vector representations of the two nodes that are connected by the edge together, maybe, if we have that, also with a vector of features that we associate to the edge itself. Okay? And so the blueprint will be mathematically as follows. We'll have so first we'll have this. So when I will use capital F, it means that I'm doing basically node level predictions. And we'll have this function that takes as input the graph representation in the form of a feature matrix and the adjusted symmetrics, and we produce as output a new matrix of the same kind as X, but now in which we will replace the vectors by new vectors. Okay, and the last one should be H. Okay. Of course, the size of this vector is something that you can set. Okay, they do not have to be of the same length as the input vectors. Okay, you can make them larger, shorter. It's up to you. Okay, but what you need to understand is that you go from a feature matrix through F, and that produces a new feature matrix. Okay. Then we'll have a function f that takes as input also a graph representation. And this lowercase f will produce now graph level predictions. And the blueprint that we'll use is to say that we'll be computing the output of f by first aggregating all the elements to all the vectors h that we can compute through this. And we'll do that over the nodes in the graph. And finally, we'll feed that to another function g. That's basically it. That's the GNN. But for this to work and for this to be permutation equivariant for node level predictions and permutation invariant for graph level predictions, we need to have some constraints on f, g, and this thing. Okay, so g actually can be any function. Typically for us, it will be a small neural network. It could be an MLP or something else. Then, okay, something I've not defined yet is how do we compute this h? Like this. So we say that hi is defined as the output of some function phi that takes as input the vector x associated to node I together with the feature matrix of the entire graph. Okay, so we have g, which can be any any function. Then we have phi, which is a function that first that will be shared across the nodes. So we'll reuse the same function phi to produce h1, h2, h3. Only the inputs of this function will change. Okay. So first it's a shared function, and what we want is for this function phi to be permutation invariant in X. If we permute the rows of X, it should not change the result. And finally, we have this thing, which is a symbol which is used often in the GNN literature to denote an aggregator, simply an aggregation function. It could be a sum, a mean, or something like this, with the property that this function should be now permutation invariant to permutations of the edge vectors of the nodes. Okay, so for example, if you say that this symbol is the mean of the vectors, if you take a mean over 10 vectors, you get some result, which is itself a vector. If you permute the vectors, and you compute the mean on the permuted vectors, you will get the same output. Okay? The reason being that the mean function is permutation invariant. Okay? Maybe I can draw also what will happen. So step by step, we say we start with a graph like this. We have some input vector first. Which could be x1, x2, x3, x4, x5. Then this graph passes through this function f to produce a new graph. Where the topology of the graph has not changed, so the connections are still the same, but what has changed are the features that we associate to each node. So now we could have maybe longer vectors. So now this would be h1, h2, h3, h4, h5. Okay, where, as I said, for example, this guy, h2, is the result of some function that takes as input x2 and x. Okay, then if you want to do, let's say, graph level predictions, we have to aggregate everything. That would be all the HI, so all these elements would enter there. That would produce a vector of some size. So this whole thing is a vector, which we feed through some function g to produce the final output y. Okay, clear for everyone so far? Okay. Okay, if so this is correct, but certainly maybe a bit too generic. And one thing in this blueprint that I've not really used are the connections. And specifically, when I define the phi function, which process or produce the new representation for each node vector, I'm saying that this phi is a function of the current vector at node 2, for example, but also of all the vectors that we associate to all the nodes in the graph. Okay? So this is maybe a bit too generic, and an assumption which is often done in graph neural network is to say, actually, because of the structure that I know between the nodes, maybe the information that I need to produce a new representation for each node should be limited to the information that I can access locally in the neighborhood of the node. Okay? And so the trick, or the assumption, will be to say we make a locality assumption in which we will limit this feature matrix to the neighborhood of node 2, okay, where calligraphic n will correspond to the set of nodes, of neighboring nodes of node 2. So in this case, node 2 is connected to 3, 1, and 5. So the neighborhood of 2 will be to n1 also, will be this. Okay, and so now I'm just passing as input not the entire feature matrix, but only the feature vectors associated to the neighbors of node 2. Yes?
Don't we have access to this information through the adjacent matrix?
Sure, but it's not passed as input to phi.
So is it easier to just pass it the adjacent matrix instead?
Yeah, but then you still have to specify which row do you access from, or what information do you use. But yes, of course you can. It's through the adjacency matrix that you will know the neighborhood of a node. That's correct. Okay, so mathematically, an inductive bias that you can have in GNN is based on locality, which is to assume that the information about a node is most relevant to its close neighbors rather than distant ones. Okay, and so we'll define this notion of a neighborhood Ni as the set of nodes J among all possible nodes in the graph for all the J's for which there is a pair ij, so for which there is an edge in the set of edges in one or the other direction. And we also include the node itself in the neighborhood. Okay, and now if we make this, if we want to enforce this and to use this inductive bias, we'll say that now we upgrade or we redesign the phi function such that it does no longer take as input the entire feature matrix, but only the feature matrix limited to the nodes in the neighborhood of I. Okay, and we'll still, so now this function will become local in a sense. It will only see information locally at I or in its neighborhood, but not everywhere in the graph. And of course, if we want everything to work, this phi function should remain permutation invariant, but now permutation invariant to x and I instead of x, the entire x. Okay, so there you see another example. There is just, so this is a figure I've reused from somewhere else, where the G that you see there is the phi that I'm using in the slides. so you can rename G to phi. But it shows you that, okay, if we have some node xb, and the neighborhood of this node is defined as all the nodes connected to B, including B itself. So the neighborhood will be all these 5 nodes. And now when we'll be computing the new vector associated to xb, it will be as a function of all these 5 vectors. Okay. All right. So what we have defined already, even though we have not defined yet how we implement phi, okay, but assume some implementation. What I will say now is that this f function, capital F function, is what I call a layer or a graph neural network layer. Yes?
Just a question for the subset of X. For the nodes that are not local, are they set to zeros, or the matrix X and I is?
You just don't pass the information at all.
But what is the structure of X and I? What it should look like?
But so yeah, okay. So if we look at so if we look at this one, H2, so H2 is a function of X2. So F of phi of X2. Okay, and then all the nodes in the neighborhood of 2, and specifically the feature matrix. So we have 1, 2, 3, 4, 2 elements. That would be X and 2. Okay, just stack all the vectors associated to each of the neighbors of node 2. If you look, for example, at this one instead, we would have that H4 is computed as a function of X4. And the feature matrix now would be made of these 3 elements. And we would have only 3 rows in this matrix. Okay. So yes, you may have, for some nodes, a lot of information that you pass through this feature matrix if the node is connected to many others. And for nodes that are isolated, for which there is only a few connections, you will have much fewer information because you will get only a few rows in this feature matrix. Okay?
The number of neighborhoods that we choose is fixed, or it will vary?
The number of neighbors? It's defined by the graph itself. It's defined by the adjacency matrix. That's an input.
We only take the first neighborhood that we found.
So you provide a graph as input, so a set of nodes and the edges, and we are just exploiting the structures of this graph. So the neighborhood are induced by the graph itself. That's not something that we pick inside the architecture. That's already given when you pass the graph. Okay, other questions? Yeah. We'll come to that. We'll see that we don't need to, because we'll be composing these things. Okay. Yes.
What is the dimension of
It's a vector of some size that we pick. Okay. So when we design phi, okay, phi will produce as output some vector. Okay. Let's say Q. and that Q is an hyperparameter that we will have to pick, exactly as we had to pick the width of a layer inside an MLP. That's something that you decide. Okay, so now I'm ready to define the concept of a layer in a graph neural network. So basically each one of these capital F functions is something that we can call a layer in the sense that it takes as input some representation of a graph and produces as output a new representation of that graph. Exactly as we had for regular, for example, fully connected layers, where you have some input represented as a vector, you feed it through a fully connected layer that produces a new representation of that information in the form of a new vector. Okay, so except that now we are defining this layer at the level of the graph representations. Okay, and so this is what you have there mathematically, where I say that the GNN layer computes a new representation of some graph x and a, okay, which you produce by just evaluating this function capital F at x and a, okay, and if we define this function capital F simply as the concatenation or the vertical stack of all the vectors produced as output of the phi function applied locally at each of the nodes of the input graph. Okay, so this is a GNN layer. Other questions? Yes?
Does it mean that we don't have many layers we want, since each edge is computed which corresponding xi?
What do you mean?
It's like we don't have the vector of edge, like the matrix edge cannot be as long as we want.
As tall as we want. Yeah, of course. The number of rows will remain equal to the number of nodes. However, the number of columns is something that you can pick and extend if you want. Cool? Because that's dependent on basically how you design this function phi. Okay? So you can set the output to be vector of any size if you want. Okay, let's take a break and we resume at 9:50 or something. Okay? Okay, we'll continue. Is everyone back? Yes. Okay. Okay, so just to give a very quick recap about what we've done so far. So we are considering neural networks that can operate on graphs. We've defined simply a graph as usual as a set of nodes and edges, connecting nodes in the first set. The representation we have considered for a graph is the one of a feature matrix X. So we associate a small or long vector to each of the nodes. And we also have access to the adjacency matrix, which tells us which nodes are connected from one to the other. We have defined several kind of tasks that we want to do on these graphs. The main ones we'll talk about today are graph level predictions. You take as input a whole graph and you want to produce some output, for example, a classification output or a regression value. Or node level predictions. You want to basically make a small prediction like classification or regression value for each of the nodes of the input graph. Okay? Then we started defining what we wanted for the requirements of this architecture. There should be first permutation equivariant to a permutation of the nodes, because permuting the ordering of the nodes does not change really the graph, only its representation. And if you want to do graph level predictions, the permutation of the nodes should not change the result, meaning we want permutation invariance to graph level predictions. Okay? Then we started defining the blueprint of these graph neural networks, and we started by this notion of a graph neural network layer, which is a function f that takes as input a representation x and a, and then produce a new representation, a new feature representation of the X matrix in the form of a new matrix such that each row corresponds to the output of some function phi, defined or taking as input the input vector associated to the node, so node I, together with the feature matrix. But then very quickly I told you that the inductive bias we would use would be based on the assumption that the information that we need to recompute the new representation of node I should only be based on local information, the information that you can access locally in the immediate neighborhood of the node. Okay, so then we've restricted the feature matrix to the feature matrix defined on the neighbors and the node itself of node I. Okay, so we have simply that a layer is just a function f that takes as input feature representation and then produce a new matrix defined simply as the evaluation of the phi function on x1 and then x neighbors of 1. Right. X2, the same function, and 2 up to the last one, x. Okay. All right. So now we see how we can actually implement phi. So we'll see three kinds of we call them propagation operators for phi. We'll see convolutional, attentional, and message passing implementations. So the first one is certainly the simplest. Is what we call the convolutional operator, which says that the output representation for the node I is given by some function phi, okay, of the input vector xi together with some aggregation of vectors that we have derived locally from each of the neighbors, okay, and which we aggregate or which we weight up or down by some coefficients ij. And so the simplest implementation of this pattern is this one, in which we say that, okay, we simply iterate over the neighbors of node I. So let's say with this again, and we look at this one, and we look at this one. So this, for which we have x, so let's call it, so we have xi, okay. So we look at all the neighbors of this node, sorry, which are these ones. Okay. And so what we do in a convolutional operator is to say you take the vectors of the neighbors independently, you linearly project them. So that's what you do there. So you take each vector xj among the neighbors of I, you linearly project them, so you pass them through a linear layer, and then you do simply a weighted mean, a mean of these vectors, of the projections. Okay? So, we take this one, So you pass it, that gives you this one, I will call it W transpose xj, and you do that for all of them. And this one too. That gives you these 4 vectors, you average them, and that gives you hi. Okay? Hi equal to. So. Okay, so each of this linear projection corresponds to one of those vectors. Then you average them, so you sum and you divide by the number of nodes in the neighborhoods, and then you have a nonlinear activation function as usual, like a value activation function, and that produces the output hi, okay, which is itself a vector, and you have set the size of this vector by setting some so the size q of the output vector depends, of course, on the dimension of the projection matrix W that we okay, and W is just a parameter that we'll learn as usual. Okay. What is important for you to understand in this aggregation mechanism is that the information that you pass to recompute the vector at node I, there is no preference towards one or the other. Okay, they are all linearly projected exactly in the same way through the same matrix, and then when you take the mean, they all account for the same amount in the weighted mean. Okay? Because you just divide by the same coefficient. Okay? And why do we call that a convolutional operator? Yeah.
So because we have the same value for each node?
Yes. Okay, that's a good point. If you remember what we've seen in a convolutional layer, we have reused the same kernel everywhere. Here we are reusing the same W matrix everywhere. Okay, we reuse the same also for this node, this node, this node, and this node. So we linearly project exactly the same way. And also in a convolutional layer, we've seen that we can reformulate that as a linear layer, okay, which is what we are doing. We are just doing a linear transformation of the input vectors. Okay. There is also this notion of locality, which is preserved here also. We considered kernels which usually were quite short, okay, but it's the same when we say that we restrict the new representation to be a function of only a limited subset of the entire input, in this case limited by the neighborhoods. Okay? The next one is the attentional operator. Okay, where we'll have something similar. Again, we will be restricting And now what we'll do is to say that hi is still a weighted mean, but now where the weights will be a function of the data. Exactly as in an attention layer, we saw that we were just implementing a weighted mean where the weights were given by the attention matrix. So we'll do that exactly in this kind of layer, where we have a nonlinear activation function of a weighted mean over the neighbors of node I, where again we'll do a linear projection, exactly as we computed values, if you remember, out of inputs in a self-attention layer. But now we'll say that the coefficients that we put at the front, they are not constant, they depend on the data. Okay, and then we'll define this alpha through some attention scoring function that will take as input xi and xj. And we produce some number which we use as the weight when you compute this weighted. And finally, the last one is the most generic one. It's what we call the message passing architecture. And so when you do that, it's as if, sorry, before I switch to the next, it's as if you say that some of the weights they are more important than others. Like these ones, but this one maybe is less important. So it will account for less, and the importance of each weight is determined by the attention function. Okay. And finally, we have the message passing function, which says that the ID is to say that we'll be computing so-called messages for each neighbors of node I. So if we are there, xi, and we are there for this neighbor xj, we will have a function which in the slide is named phi, which will compute a message, so we call that nij, okay, so which take these two vectors, produce another vector, nij. Okay, so we do that for all nodes in the neighborhood. Okay, that gives us 3 messages in this case, and then we do an aggregation of these messages. And so we say that hi is equal to some function phi that takes as input xi and the aggregation of the messages through some operator which is permutation invariant. Okay, where phi can be any neural network, this phi can be a neural network, where this aggregator is something which is permutation invariant, like the mean or the sum, and these messages have been computed in this way by some function calligraphic phi, which can be anything, like a neural network also. Okay, so this is just a regular neural network. This is also a regular neural network, and this is something which is just permutation invariant. Okay, so this is the most generic kind of functions for the operator we can have because it has the least constraints, and you can go from this one to the other two depending on how you implement these two layers. Okay, but if you say these two guys they are just regular neural networks, it's also one of the most difficult architectures to train efficiently. What works usually the best are the attentional operators, which remain easy and still very powerful. Questions on this? Yeah.
Just so, are the previous method a message passing form or not? I don't. So we said that it's the more generic form.
Yes.
And I don't. So, for example, for the convolutional, it's just a special case of message passing.
Yes. Yes. Just like an MLP is like the most generic architecture in a sense, from which you can derive, for example, the CNN or the convolutional layers, or more precisely, fully connected layers. They are more general than convolutional layers. I'm just saying exactly the same thing. If you take message passing operators, they are strictly more powerful than convolutional operators. They can pre-implement everything you can express as convolutional operators and more. Okay, and the same for message passing. With regards to attentional, it's also more powerful than attention. Okay, but exactly in the same way as it's difficult to train MLP on images, depending on the kind of data that you have, it might be much more difficult to train these very generic architectures because you are not maybe exploiting inductive biases that would have made sense for your data and for which either convolutional or attentional operators would have been much more appropriate. Okay. Questions? Okay, now we are almost ready to see. We have everything now almost to design proper GNNs. Okay, so now we'll take all the bricks we have seen and compose them. Okay, so let's say we start with some graph, always the same one today, like this. That's our input in the form of this representation of feature matrix and the adjacency matrix. Okay. You can pick any of these layers, okay? They will define some capital F function. And will produce, as output, a new representation of the graph, which I will call H, okay? Where H, this matrix H, is the matrix where I've just put all together the vector H that I'm producing as output of the phi functions. Okay? Okay? And so the first composition that I can make is, like in an MLP or in a CNN, I can say that I will stack in parallel several of these functions, of these layers. So let's call this one F1, this will be F2, sorry. That produce H1, and this one H2. And I can stack vertically many of those. HK. Okay, so that means for each node of the, so it's as if I was replicating the graph, and for each replicate, I have at each node some vector. And I do the same here. And so on. But since I'm producing these vectors using distinct functions, of course the vectors from one replicate to the other, they are not the same. Okay? So where have we done something very similar to that? Yes, why in CNN?
Stack multiple kernels together.
Yes, so if you remember our convolutional layer, it's defined over multiple kernels, but each of them independently takes an image, instead of a graph, it takes an image and produces a new feature map, a new image, which is a function of the kernel we've used, which is a function of some kernel. Okay? And then if we say we have multiple kernels in a convolutional layers, then we are just stacking several of these representations of the image, okay, which are all different, okay, to produce the final output, which is just, like in a CNN, the concatenation of all these feature representations. Okay, so then we can just aggregate everything. For example, we can concatenate. So this symbol means I concatenate along the channels. To obtain now a new graph. Where each row of this matrix is the concatenation of the rows of the HK matrices. So we've seen that in CNN, in convolutional layers, but we have seen that elsewhere also. Yeah, when we talked about the multi-head self-attention, we are just replicating in parallel several self-attention mechanisms with their own weights, and then we concatenate everything. That's exactly the same mechanism. So instead of having this self-attention, produce new representation of the tokens and then concatenate everything, we are just doing that now at the level of graphs. Okay, so this is the equivalent of a layer, like a convolutional layer or a block, in the case of multi-head self-attention blocks. And then, as usual, if you can compose these primitives in parallel, then you can guess that you can also compose them in series. Okay, and say that now this guy that we have there, I will use this new representation as input to several of these parallel layers. And so on. Which I can aggregate again. Okay. Yet another representation of the graph. Okay, so this is what I explained in the slides. First, in the case of the parallel composition, so we can compose any of these 3 layers in parallel. Okay, each one of these instances of the layer will produce some HK feature matrix, which we can then concatenate along the channel dimension to produce the final H matrix, this one. Okay, and this is another representation where what you see there would be the case of 3 attentional layers combined in parallel. So you have 3 colors, one for each of the 3 attentional layers. And so if we are considering node 1, we have attention weights for the first block in green. And so you have the alpha coefficients that we compute through the attention. That produces a new vector, H for H, and for this specific attentional layer. And then we do the same for the blue and the purple. And then we either concatenate, as I did there. You can concatenate all these vectors that are computed in parallel, but you could also aggregate them using another operator like the average, if you want. Yes?
We use different types of layers, like we use convolutional and attentional.
Yeah. If you think that's a good idea, that's something you can do. Usually we keep everything more homogeneous, unless really you have a good reason to do something else. But usually we don't have a good idea of what should really be done by the neural network. So we let usually the neural network discover what it should do and what it should compute and then recombine in the layers. Questions on this? So this was for the parallel composition, and then the sequential composition, which is just to say, okay, these parallel layers, they produce just a new representation in the form of a feature matrix and an adjacency matrix, which, by the way, in this case, it remains the same always. There are other layers which can also change the adjacency matrix, like the equivalent of pooling layers, but for graphs. I will not talk about that, but you should know that these things, they exist, and they will have then an effect on A and H. But so, regarding the sequential composition, the layers can be stacked in series to form now deep graph neural networks, not shallow graph neural networks. And we are just saying that the output of a layer will be used as the input of the next layer. Okay? Exactly as we did also in CNNs and transformers, where in CNN we were stacking in series several convolutions, several convolutional layers. And for transformer, we were stacking several of these multi-head self-attention blocks. Okay? What is interesting also to notice? So let's say we use convolutional GNN layers everywhere. Okay. Can you tell me about what would be if we take this node? What would be the equivalent of its receptive field? Meaning, what is information which is used in the input to compute this vector? Yeah.
It's the neighborhood.
Yeah, it's the neighborhood. So this node, this new vector H4, I think it was, or 5, is computed from the information that we can gather from the neighborhood of this node, which is this. Okay. So that's the receptive field. Exactly as I talked about receptive field in convolutional layers. Now, what about the receptive field of this one? Yeah. Exactly. So so let's do it step by step. So the receptive field of this node with respect to its parent is what? Is this? Sorry. That's this one too. This. That's this. So this. Okay. That's the immediate receptive field, but when it comes to the effective receptive field, with respect to the information used from the input, then we have to backtrack again and consider, okay, what is the receptive field of each one of these elements? So the receptive, see if we do that for this one only. So the receptive field of this one is this. The receptive field of this one is this. The receptive field of this one will be yeah, this one too. And of this one would be these two. Okay, so the union of all these things, of all of these sets, is the effective receptive field, which in this case would correspond to actually all nodes in the network. Okay, so that would be the effective receptive field with respect to the input. Okay, so we have the same, yes?
It's a set of elements.
Is the union. Yeah. I'm just basically reasoning about what is the part of the input graph which is used effectively to compute this quantity at this part of the GNN. Okay, and so that's really equivalent of what we had in CNNs. If you remember, when we talked about for example, the VGG architecture, I've showed you the fact that when you look at the information which is used deeper and deeper in the network, you are increasing the effective receptive field of this element. Okay, and if you remember, the increase is linear in the number of layers that you stack if you just have convolutional layers, and if you mix convolutions with pooling layers, then the size of the reflective field was growing, in this case, exponentially fast in the size in the number of layers. So we have really the same with this kind of usage of more and more information as if it was propagating. So if you look at this graph, and if you just consider a one-layer GNN, so we stop there. And if we look at some node in yellow, and we reason about the nodes that are used to compute this yellow node, we would just be using the immediate neighborhood of the node in red. Okay, but now if we compose another layer in series, then the vector associated to the yellow node would be a function of the immediate neighbors of that node and of the immediate neighbors of the immediate neighbors. Okay? So then you would just basically do it's as if you were doing a two-step breadth-first search to collect all the nodes. And basically all the information that you have is effectively used to compute the yellow one. And if you look at a three-layer GNN, you see that it's growing very quickly, in this case for this graph. Okay? So of course, how fast information will spread as you compose layers in series will depend on the connectivity of the graph. If you have a graph for which any two nodes can be not connected, but connected through a path very quickly, then you will have a very quick spread of information. If on the other hand you have long paths on average between two nodes, then it will take deeper GNN if you want to connect everything to everything. Okay? But maybe it is answering someone questions from before the break. How do we define the neighborhoods? This one, do we define them only from the topology of the graph? And that's what we do. But that's not really a limitation, because if we then compose this layer in series, it's as if we were increasing the size of this set of neighbors. Okay. Exactly as we did for convolutional layers, we said it's fine actually to use small kernels, meaning it's fine to use small neighboring sets, provided that we stack these layers in series, because that will be equivalent to just increasing the size of this neighboring set or increasing the size of the receptive field. Questions? No? Okay. And finally, the last element that we need is to basically think for 2 seconds about how we implement the output layer. And so usually the final step is to take after this operation, we have again a new representation HA. Okay. And if we want to classify, for example, or produce some regression value for this graph, we need, so we are in the case of a graph level prediction, we need the graph level predictions to be permutation invariant to the node ordering. Okay, so that means we need, or one way to achieve that would be to aggregate the rows of this matrix using an aggregation function which is permutation invariant. Okay? And so simply, very often what we do is to say that we compute H bar as the aggregation of Hi vectors in H. Okay? Over all the elements in the group. Well, again, this aggregation function is just something which is permutation invariant, which could be as simple as the mean or the sum or something like this. Yes?
Is it true that only the first stack of layers should be invariant to the permutation?
No. These layers, they should not be invariant. They should be equivariant to permutations.
And the other?
It's only if, because up to there, everything remains at the node level. So it's as if we are doing node level predictions. We maintain the structure of the graph. We maintain vectors for each node. Okay, so if we permute the ordering, everything should permute accordingly. And it's only there, if we want to do graph level predictions, then this part should be permutation invariant. Okay, but we achieve that trivially by just taking the sum or mean for these vectors. Okay, and once we have H bar, well, we say that if this, we fall back now to the regular tabular format for which we have a vector that represents a graph, and we feed that to a neural network to produce the output. Okay, and this neural network can be anything that we have seen before, like an NLP, a CNN, a transformer, whatever. Okay. How do we train this neural network? Yeah, so as usual, it's just a regular neural network. It's a composition of functions that are all differentiable. So depending on the task we level us, then we differentiate the computation of the predictions with respect to the parameters, and we are good to go. Okay? Okay, so now I will consider two or a few actually special cases. The first one, which is interesting, is the case where you have graphs without any edges. So when the set of edges is empty, you just have nodes, in a set. Okay, and if you want to do task node level or graph level predictions, it's as if actually we're now doing. So in the case of node level, we are doing element level predictions. And if we are doing graph level predictions on this graph without any edge, it's as if we are doing predictions on sets. Okay, mathematically sets. Okay, so these GNNs, you can use them as soon as you have information which is really a set of things, and you want to process this set all at once as a single object, you can use a GNN without any edges. Okay, so mathematically, when the set of edges is empty, the graph reduces to this set of isolated nodes. In this case, we have that the set of nodes, ni for any I, is just made of the node itself. Okay. In this case, what will happen is that all these propagation operators, they will generate to just one element, okay, the node itself. That you apply in isolation to each node. Okay, because now, since there is no edge, there is no communication between the nodes. Okay, so effectively, this GNN, this function G of the aggregation of the output of this operator, just degenerates to the aggregation of some function phi that you apply locally at I and only there. Okay, and this resulting architecture is what we call a deep set. Okay, but which is nothing else than a special case of a GNN for graphs that are empty. Okay. The opposite case is when you have a complete graph where all nodes are connected to one another. Okay, which could be the case because really you have graphs that you think are fully connected, or because actually you presume that the nodes are connected, but you don't know if they are actually connected. Okay? So in this case, instead of making strong assumptions, you just say, I don't know, and then I think everything is connected. So I fill in entirely the adjacency matrix with ones, and I will let the neural network figure out if there are actually important connections between the nodes. Okay? So when nodes are expected to have a relational structures, but the edges are basically unknown, the common assumption is to say that all nodes are connected to each other, in which case what we'll have is that the set of neighbors for any node is the set of nodes itself. Okay, and we'll also make the assumption that there is no stronger or weaker edges between nodes. We just assume they may exist, and we let the neural network figure that out.
I have a question.
Yeah.
In how many steps will the network figure out the edges that it can put in the garbage? Because in really big network, it will induce a lot of computation.
Yes. Yeah.
And so,
I mean, as soon as the graph is complete. So for each node, you have to iterate over all neighbors, so the cost is already quadratic.
and it could be quadratic for a lot of steps, or in, I don't know, in 3 steps.
I mean, the edges will remain there at every step of the architecture, so the cost will not disappear.
Okay, so at some point we will not suppose that if the weight is too low, we can...
No. Mm-hmm. Okay, and then, so in this special case, the case of complete graphs, it's interesting to think also about what happens then to convolutional GNN layers and then attentional layers. So for the case of GNN layers, what we have, since all nodes are connected to one another through this, by doing this, we have that this quantity actually is the same at every node. Okay, so this quantity is actually constant across the node, which is a bit useless. And so this quantity there will remain the same. And so if it's the same everywhere, we can actually remove it. It does not provide any information specifically at node I, so we can remove it. And so in this case, using a convolutional layer is not really useful or appropriate because it's as if we were just computing some local function phi at each of the vectors associated to each node. However, what is more interesting is the case of attentional layers. In the case of attentional layers, we'll have that these attention scores, they are computed not over the neighbors of I, but over the entire set of nodes. And for each node, we have this attention score, okay, which you can interpret really now as some strength that you associate to this edge connecting or possibly connecting node I and J. And then you have this local computation of or transformation of the vectors. And this should remind you of what we have seen last week and the week before. This is exactly a self-attention layer. A self-attention layer is a weighted mean where the weights are data dependent of values that you compute usually by doing a linear projection of the inputs. Okay? So in the case of self-attentions, if you say that in the case of a self-attention layer, you have tokens as input. These tokens, they are just a set of tokens. Okay? And by default, we assume that these tokens, they can relate to one another. So it's as if you were putting this token inside a graph where nodes are equal to token, and we don't make any assumptions about the edges. So we say that this graph is completely connected. Okay? Any token can attend to the other. And then we were computing attention score, so how important each token for each other by doing that. Then for each token, we were computing a linear projection, a value function. And then we were saying, we say that the output representation for each token is the weighted mean, where the weights are the attention score of the values that you associate to each token, which is exactly what you have there in this formula. Okay, so again, this is just to show you these GNN layers, they are actually quite generic. You can express convolutional layers, but also self-attention layers. Okay? And finally, the last special case is when you say that an image is a graph. So if you consider pixels as nodes, and then you say two nodes, meaning two pixels are connected if in the actual image they are next to each other, then you obtain some adjacency matrix. Okay? And then, so that gives you this A, this initial A. And then in X you associate, let's say, a very small vector which maybe initially just encode the three channels, red, green, and blue. Okay? But then you do this. What you will be effectively doing is the same as what a convolutional neural network is doing, but expressed as graphs. Okay? So I'm just saying, GNNs, they are also convolutional neural networks. So everything that a CNN can do can be expressed as a GNN. And similarly, everything that a transformer can do can be expressed as a GNN. Questions? Yeah.
But in the end, using graphs instead of just regular implementation of attention or convolutional layers really increase the performances of the algorithms?
What do you mean performance? The quality of the results, or how long does it take to compute the results?
Both.
I mean, mathematically they are equivalent, so in terms of quality of results, it should be the same. However, if you take an implementation of graph neural networks, that will usually be much less efficient than an implementation which is tailored, for example, for images or for tokens. Yeah.
As the convolutional neural network is a special case of the graph neural network, define kernel size is like defining a deep enough graph neural network or putting edges where
Exactly. Yeah, exactly. So you can have the equivalent of the size of the kernel by just depending on the connectivity that you have between the pixels. So, for example, for this connectivity, we would not have actually the equivalent of a kernel because we are missing the diagonal connections between the pixels, for example. But if you add them, then you have something very close to the CNN. Yeah.
And as we had for CNN, we can perform pooling for graph neural.
Exactly. So that's something I mentioned quickly, but I don't have it in the slides. But if you have, let's say, this and others, okay, like this, you can define the equivalent of pooling layers but on graphs. There are various algorithms, but they are not that interesting. But basically, they will aggregate the nodes somehow, maybe in this way, and maybe you could have overlapping also sets. And then you have as output of the pooling layer, maybe this first, a new node, which is the pooling of these three nodes in the first group. Then this node, which corresponds to the aggregation of these ones, and then this node, which is the aggregation of these ones. And then you have to think about how will you then build edges. You can say that you connect two groups if they share connections. So, for example, these two groups will be connected because there is an edge from one node of the first group to some other node of the second group. However, for example, this group is not connected to this one. There is no pair of nodes which are connected, and here we have a connection. Okay, so this will be the equivalent of a pooling layer over graphs. Then you obtain a new matrix for the features and a new matrix for the adjacency.
But for the CNN, the goal of pooling was to increase the receptive field, but here, given the graph neural network, it's already.
But actually, you can. That's a good point. If you take a convolution and then you stack several convolutions, that's something you can do, huh? Which is done in some very standard architecture. But the effect, or what you should understand, is that if you do that without pulling layers in between, the size of the receptive field will only increase linearly with the depth of the network. If you want to reach much faster different regions of the input image, you need to pool the representation, pool the image, or pool the graphs, and then very quickly you will reach much further away when you do the second convolution or the second GNN layer in the case of GNNs. Okay. Okay, so then let me finish with a few nice applications which have been made possible because of this architecture. The first one, which I found quite interesting, is the case of applying machine learning or deep learning to discover new antibiotics. This is the example I was taking at the beginning of the class this morning. And the goal is to say, okay, I will have a graph neural network that takes as input a molecule, which is represented as a graph. Nodes are atoms, and edges correspond to bonds connecting two atoms. And the goal of this neural network is to say, for example, if this molecule would have a pharmacological effect, for example, would it inhibit the growth of some bacteria? Okay? If that's the case, then that means the molecule is actually an antibiotic, okay, which is something very important. But of course, as I was explaining, there is no way you could just, in a wet lab, evaluate the quality of all possible molecules. There are just too many. So we need to filter out and only keep the ones that are possibly effective, the ones that are the most promising. Yes, but if you have, and that's something we have, data sets for which you have molecules on the one side and then the quality, I would say, or the effect of the drug as output, then you can learn a classifier, in this case, a graph level, that would be a graph level task that takes as input this graph representing the molecule and would tell us if whether or not these molecules is interesting. And so this is what they did in this paper, where they started from a huge chemical space of possible molecules in the order of millions, which is already small, actually, because you have many, many more molecules that exist, 10 to the 60. But so they consider a small set of a few millions of them. And then they reduce that to just a couple of hundreds by just learning a classifier, making predictions for every one of these millions of molecules, keeping the top most promising molecules, and then effectively then assessing the quality of the molecule in the real world. And because of that, they've discovered actually a new antibiotic, allicin, which was shown to be very potent, very effective to prevent the growth, in this case, of Escherichia coli, which is one of the most common bacteria. Again, just using GNNs. And of course, the data set. Another example, this time in vision, in computer vision. So when we talked in lecture 6 about computer vision tasks, one of the tasks was to do detection in images. So where we wanted to locate objects in the form of bounding boxes that would be as tight as possible around the object that we wanted to detect. That's nice for images, but when it comes to vision, there are many other instruments that we can use than regular RGB cameras. One of those, for example, is the case of LiDARs, or basically instruments that give you point clouds as outputs. Okay, and these point clouds, they are basically raw representation of 3D scenes. And one task then that you could maybe want to achieve is to try to do object detection now in these 3D scenes, but over directly point clouds. Okay, and that's the thing you can do, again, using a GNN, but a GNN now which looks very similar, for example, to the YOLO architecture, except that all the elements of YOLO have been replaced by GNN layers. But so you would start with this very raw point cloud representation. You would build a graph out of it. So basically, you could say I'm connecting points that are close to one another. Maybe you could also remove some of the points in regions of high density. I mean, whatever. You get a graph. Then you feed this graph to a point GNN, which takes this point cloud as input. And then what does it do? It does object detection. So you have first, let's take this part. So you have the graph and its nodes. You compute vectors for each of them. And that's basically the equivalent of, let's say, this part, or the var5 function mentioned in the slides. Then you aggregate using one of the possible operators we have seen. That gives you a vector representation for each node, and that's what you use to update and produce a new graph representations for each of the nodes. Here you also see that you have this arrow going below, which is just a skip connection. Of course, you can insert skip connections between everything if you want. And so you can repeat that for t iterations, or for t layers. And once you're done, once you are at the end, you can just say, now I will be making graph level predictions, but my outputs, they are not just regular scalar values, they are what I'm doing usually sorry. So no, in this case, it would be node level predictions. And so you associate a class for each point, each node, together with coordinates. Okay, and then you could have further algorithms, maybe to remove some of these boxes, which are not really important, exactly as we did with YOLO. YOLO was producing many boxes and many predictions, and we were only keeping the ones that were for which the network was the most confident. We're removing the overlapping predictions and so on and so forth. You can also do that, but now in 3D. Okay, and this is what you get there. So you get all these boxes. You have some post-processing to merge the boxes, to do non-maximum suppression, and at the end you get just a small set of outputs which correspond to the predictions. Okay. Another application is the case of Google Maps, just to show you like the variety of things we can do with the same architecture. So I don't know if you have ever wondered if you try to estimate the time it will take you to go from A to B in Google Maps, how things are actually computed. It's actually using a GNN below. And it's using a GNN to assess the time it will take. So let's say you have a first some road. You are and you want to reach A, and you are in B, and maybe there is some other road going like this, and maybe you can do like this. Okay. So actually the road network is divided into small segments. Maybe like this. And these segments, you can basically now view them as nodes in a graph. Okay, where you would have a node there, a node there, a node there, a node there, and two nodes are connected if they are connected physically in the real world. Okay, and so now the question is, okay, how long will it take to traverse, for example, this segment? And how long will it take to traverse this one, and this one, and this one, and this one, and this one? And all these segments basically on the planet. That's a node level classification task. Or an edge level classification, depending on how you formulate the problem. But you need basically to make these predictions at the level of every node or the level of every edge. Okay? And why is it interesting to do that using a graph neural network? Because of course, for example, if you have some congestion with traffic on this road, that will have an effect on what's going on there. And so the segment that you would have to traverse and maybe the following ones also will be affected. Okay, so you have a spread of information of effect through the topology of the graph. Okay, and so you can just inform the neural network about this topology, and if that's really useful to make correct predictions, it will leverage that. That's exactly what they do. So they do that to basically, they use a GNN, this case of the form of the message passing GNN, where you see they transform the road into a graph with vectors, then the GNN to recompute, and then from these vectors to provide estimates of the current traversal time of these segments. And once you know basically the cost of passing through each node, then you can run a classical algorithm to find the shortest path going from A to B, while minimizing the total cost to reach the destination. Okay, so the GNN precisely is used to estimate the cost of traversing a segment. Yes?
What do we use if we have a variant size of graphs? Do we use computers?
It's not an issue. Why do you think it's an issue? That's a good question. But actually, these neural networks, they can work on any graph. You can train them on graphs of size 3, 5, 10, all at once, and then make predictions for size 7, 20, 100. And there is nowhere in this architecture a dependence on the number of nodes.
But if, for example, the learnable parameter W
Yes.
is of dimension.
No, because you just linearly project this vector, which is fixed. Okay. For example, you would have, I don't know, x would be vector of size d. The vector that you associate to each node will be of size d. And then you say w is a vector of size, it's a matrix of size transpose, so d times q.
So it depends on the size of A.
No, where?
D.
Yeah, but d is the size of the vectors that you associate to each node.
Oh, it's a design choice.
Yes.
Okay.
Okay, but nowhere you see there a letter which corresponds to the number of nodes you would have in the graph. D is the size of this vector. Okay, so if you have, for example, this graph with 5 nodes, you have 5 d-dimensional vectors. Okay, a next application is the case of physical simulators in physics. And so this is, I think, a nice illustration of what you can also do with GNNs. In this case, it's used to basically simulate the evolution of a fluid, which you have represented as a graph of particles. And so the idea is to say, okay, I have a graph of particles, which you see there, and I will use a GNN to simulate the evolution of these particles. Okay, this is what we call particle-based simulators, except that now this particle-based simulator will be implemented as a graph neural network. And it goes in 3 steps. So you start from a set of particles, which you encode. So you compute a new representation of each particle. Then you have a processor, and the processor is taking as input a set of particles and producing as output another set of particles. This is a node-level prediction task, where you try to predict the next state given the current state. And this processor is implemented as a graph neural network. This is what is referred to here as GN for graph neural network. And you just chain M of them, so you have M layers. In this case, again, with skip connections. This one is implemented with message passing. And that produces as output some vector from which then, that produces as output a vector for each particle, for which then you decode, for example, the displacement of each particle, and that's the final output. And then you can iterate like this to produce the next time step, and the one after, and the one after, and so on and so forth. Okay? So this is just to show you an example of a graph neural network which has been trained to reproduce a physical simulator. So this is effectively what we call an emulator, but implemented by a graph neural network. Okay, so this simulation is produced by a graph neural network. And this is the ground truth data which is used to train the neural network used on the right. And the trick is to say your fluid is made of particles, and then you will just simulate the displacement of each of them, depending also on the physics that you assume, on the viscosity of the particles. Maybe you could have also several materials, so particles of different kinds. And basically all of this information are things that you provide together with these small vectors, like viscosity, positions, and so on and so forth. Okay, so in this neural network there is no fluid mechanics equation. It's just these two blackboards, and you can do that with them. But of course you need the training data, in this case, which is simulated using these physical equations. But why are people interested in this problem specifically? The reason is that now that you have a neural network that maybe is good enough to reproduce the physics of the original simulator, this emulator is much faster. It's a neural network that you can run on GPU, and it will produce videos in seconds instead of hours by just doing everything in parallel on the GPU. Also, the emulator that you get is now a neural network, so everything will also be differentiable. So now if you want to do design of things, like the 3D wing example that I've shown you, if you remember when we talked about automatic differentiation, but for that to happen, you need an emulator, a simulator which is differentiable, which you could also obtain in this way. Okay, and finally, yet another application of GNN. This one is for weather forecasting. This is the case of GraphCast, which is a deep learning model used to predict the weather for the next 2 weeks. And again, this is done using this idea of having an emulator, meaning a graph neural network which will predict the next state of a system, except that now the system is not just this fluid in a box, it's the entire, in this case, atmosphere. So you can view the modeling of the model of the atmosphere as a big onion with several layers, and at each layer is itself a very fine mesh of pixels, and then you associate at each position physical quantities like temperature, humidity, speed of wind, and so on. And usually what we do for regular numeric predictions of the weather, we use numerical models that implement physical equations to predict what will happen next in the next hours, in the next days. This is very slow, but we can accelerate that if we replace this part by a neural network, which will take the current state as input, which is very big in this case, and then we predict the next state as output. But if for this to work, we need to have a meaningful and appropriate representation of the state, which in this case is very naturally represented as a graph. You have this kind of 3D volume of the sphere, or the atmospheric layers. You have immediate connections, immediate effects between neighboring pixels, like around but also above and below. And so you can say this is just a graph for which I know the topology, and I will just feed everything then to a GNN to produce vectors that you associate to each pixels, in this case the new states at the next time step, which you will decode eventually to produce the offset, the displacement, the changes of the state of the atmospheres, and then you can unroll this emulation forward in time to produce forecasts. Okay? And these days, graph neural networks or neural networks for weather forecasting are producing results that are more accurate than physical models and faster. Questions? No? Okay, then that's it for today. Thank you.